Good morning, everyone. So let's start our seminar. So today we are excited to have the Dr. Baochun Li here. Dr. Baochun Li is a full professor at the University of Toronto. So he is the fellow of the Canadian Academy of Engineering, a fellow of the Engineering Institute of Canada, and also a fellow of Archibald. So his research focuses on the cloud computing, security and privacy, distributed machine learning, federated learning. So Dr. Baochun Li is also my postdoc advisor. So today I'm very happy to have him here. So I would like to bring attention to the figure in his slides. So you will feel exciting for that. Very beautiful. You cannot imagine that all the figure he hand draw by himself. Okay, so please join me to welcome Dr. Li.
All right, it's my great pleasure to be here today, and thank you so much for the introduction. Today, I'm going to just try to answer a very simple question. Does federated learning preserve data privacy? Why would I ask this question? Well, let's get started from federated learning. This is a very simple idea. We try to train where data is located. And it has increased dramatically over the past several years since 2017 when this idea is created, all the way to last year. As you can see, we're just looking for, this is an advanced Google Scholar search, we're just looking for the term federated learning in the title. So the actual number of papers might be even more. If you don't have that term in the title, we don't count it. But still, you can see in an accelerated pace of the number of papers published in this area. But why the popularity? Why do we care so much about federated learning as a community around the world? Well, I would say it's just my personal take of this question. Maybe the reason for that is because it is the only practical way to keep the data private while we have multiple clients collaborating to train a shared global model. Maybe it's the only way of doing this. So whenever you need to keep the data private and whenever you have more than one client that wanted to collaborate and train a model and you cannot let the data leave the client, then probably this is the only practical way. So the idea of federated learning, just want to have a very quick review, is actually quite simple and it's actually almost trivial. The idea is very easy to understand. Basically, you have the server and you have a couple of clients and you wanted to let the clients collaborate to train on their own local private data. And what we're doing is that we're sending the model from the server to the client, and then we let the client train maybe for a couple of epochs, each epoch containing iterations going through all of the data in the data set, and then send the model updates after the local training back to the server so that the server can just aggregate these model updates. So that's a very simple idea. This is actually a little bit too simple in that sense. Now, more recently, we actually have probably better ideas of doing this. Probably we don't have to aggregate on the server. Maybe we don't need a server. Maybe there are some, but those, I believe, are just variants of this idea. And we basically still have to let the clients collaborate, so we just call them all federated learning. So let's start from this classic idea back in 2017. The problem here is that there are quite a lot of papers that claim that the original motivation of federated learning is not valid. Our motivation, as you remember, is that we need to train on private data and we want to keep the privacy of data. But there are quite a lot of papers claiming in the recent years that you cannot keep the data private. The private data, there is a real possibility for the server, if the server is untrusted, or very likely the server is untrusted, the data can be reconstructed. And there are quite a few papers. For example, there's something called the gradient leakage attack. Originally, the gradient leakage attack is on the centralized training situation. In the context of centralized machine learning training, And we're going to get to this idea very quickly. But there are quite a lot of papers in the past 5 years, starting from 2020, published in Europe, CVPR, EMNLP, and so on. These are the papers basically saying the original idea of gradient leakage attacks that actually was true for centralized machine learning training is also true for federated learning, which basically says at a very high level that the data can be reconstructed, it can be leaked. So the question is that true? Or are these papers making a valid claim? There are quite a lot of papers which, is actually, make it really quite convincing because there are quite a lot of papers, a lot of researchers believing that this is true. So I would like to get back to the very original question. Before these papers are published, are these papers convincing? Does federated learning really preserve the privacy of raw data on each client? Can we reconstruct the data on the server? So let's take a look at the gradient leakage attack. So originally, as I mentioned, this is proposed for the centralized machine learning training. So the question here is, what are these attacks, gradient leakage attacks? Well, originally you used the data set in this machine learning training loop, and you get the actual gradients. And the gradient leakage attack basically says you could actually try to, get the data back. So before we get to that, let's try to see how we actually do the training in the forward, in the original training case. Well, the idea is very simple. You have the data set, you go through the model, you have the prediction, and you produce the loss using the prediction and the label in your data set. This is a classic supervised machine learning. And then you will actually produce the gradient. Once you have the gradient, you basically update the model using a learning rate and the production of the learning rate and the gradient. It's a very simple idea. It's a simplified version of what's going on right now in our training loops, but that's the idea. And then we have the model update. So what about the gradient leakage attacks? Well, it's pretty simple. You have the gradients. They claim that you can actually get the data back. So how do we do that? Well, the idea is also kind of simple, but it is surprisingly effective. So what you do is that you still have the model, and then you use the dummy data, X prime, and you send the dummy data into the model to get your prediction. And then you use the dummy label and the prediction, and you produce the loss value using the same idea as before. You get the gradients, and then you try to optimize your dummy data and the dummy label iteratively so that you minimize the distance between the actual gradients that we believe that the attackers have and the gradients that you produce. So that's the basic idea. It's basically an iterative optimization. And that, surprisingly, was actually quite effective of getting the original dummy data. We're going to show some examples later on. So now the question is, if, assuming this is effective in the original machine learning, centralized machine learning case, is it still effective in federated learning? Can we steal the client's data in the federated learning setting? So the question is answered by the papers that we just listed, quite a lot of papers. They basically said it's still valid. Yes, we can steal client's data in the federated learning setting. And I would like to question that. And a lot of them basically, the papers, they basically say that the client's gradients are shared with the server. And that is the assumption that these papers make. And I would claim that this assumption is not true. This is not a valid assumption. And the reason for that is because we are not really sending the gradients to the server. We're actually sending the model updates, as you have seen from our original introduction to the basic idea of federated learning. We're not sending gradients, and model updates, we believe, they're not the same as gradients. So some papers in the past, they also realized this. This is not hard to realize that model updates, they're actually the combination of multiple iterations and even multiple epochs, and they're not the same as the gradient, which is the result of one iteration. So they basically said, sure, it's not the gradient, but we're basically just need to divide the learning rate and we can get the gradient. But still, that is not true if we have multiple iterations. And there are multiple steps of gradient descent. In our typical local training, we have multiple iterations in each epoch, and we typically have multiple epochs in the local training. And the reason for that is very simple, actually. The reason that we do this, multiple iterations, local training, is because we don't want to send these model updates very often. We want to send these model updates relatively infrequently because it's a huge amount of communication overhead. We don't want to communicate that often. So there are multiple steps locally, so which means that we're going to go through a lot of data samples. We're going to have a batch size that is less than the data sample, and then we're going to have more epochs. And on top of that, we have even more reasons to believe that the model updates are not the same as the gradients because we're using more sophisticated gradient descent algorithms than simply just multiply by the learning rate and get the model update for every single iteration. We have the momentum, we have the weight decay, we even have in most cases the learning rate scheduler, which means that the learning rate itself changes across different iterations. And that is something that makes it much more sophisticated, and it's actually much harder to get the gradients from the model updates, unlike some of the claims in existing papers in the literature. So what we have here is that we have also researchers realizing this, and what they said is, fine, we don't get the gradients, that's okay, but we still have the model updates. And with the model updates, what we can do is that we can revise our original gradient leakage stack rather than minimizing the distance between the actual gradients we receive and the gradients we compute. We basically revise it so that it is minimizing the distance between the actual model updates that we receive and the actual model updates that we compute. But is that valid? Well, we believe that this is also a very problematic claim that you can actually do this. Because if you want to get the model update, you will have to know a lot of things about the training loop on the client side. And if you assume that you know them, sure, then you can do this, but most likely you don't. For example, you're going to have to know the learning rate scheduler. You have to know what exactly is going on over there. And that's typically not known. But assuming that we have all of those assumptions, valid, that is assumed by the original papers, we also discovered something else interesting. So here's an example. We have the ground truth. This is a classic, CIFAR-10 data set, and we have the ground truth. And we have different random seeds, random seed number 1 and 2 and 3. And we just wanted to run it in a completely centralized setting, no federated learning, nothing. And we just wanted to, try to reverse engineer and get the actual regional image reconstructed. So as you can see, different random seeds, there are different effectiveness. Some of the random seeds, such as random seed number 2, is a little bit more effective than seed 1 and seed 3, but relatively they're quite effective. They can reconstruct most of the images. So that's something that is the actual result of the original gradient leakage paper, gradient leakage attack paper. But here's one little thing that most people did not notice, that this is actually something that is from the original paper, that we're using an untrained neural network model, completely untrained, and with explicit initialization, in the sense that we explicitly initialize the random weights in that untrained model to be something with a much wider range of values for each one of these weights. And if we actually change that assumption, which is kind of weird, why do we have to assume that? Most likely our untrained neural network model will be directly coming out of PyTorch, for example. So we don't really explicitly initialize the weights to help the attackers. That's not something that we typically do. But if we remove that assumption, we use the default PyTorch initialization, and we immediately get much worse results. And that's something that is interesting in the sense that even the original gradient leakage attack paper, they're making assumptions that are not valid in the real world. And we also found out that if we actually try to train the network using a pre-trained weights, even with the same data, we don't even have any success, no matter what is the random seed. Even if we assume that we're not in the federated learning setting, but going back to the original centralized machine learning paper. But still, we wanted to do some kind of defense. Assuming that the attacks might be successful, we want to have a defense. Most papers, what they do is that they start from the assumption that the attacks are successful, and then they propose a very heavyweight defense. And we wanted to propose some kind of a defense that is lightweight. And we wanted to make sure that it's sufficient, good enough to launch this defense, and also self-adaptive so that we could actually try to have a lightweight defense. And in terms of sufficiency, all we need to do is that we need to selectively perturb the weights the updates that we send to the server. We don't have to perturb all of them, and that would be all good enough. It will be sufficient. And then to do that, we propose to use the diagonal of the Fisher information matrix, which basically helps us to select the actual weights to perturb. And then we also wanted to have different intensity in terms of sufficiency. Remember that the range of weight values in the original paper, if it's a much larger range in the initialization of the explicit initialization of the random initial model, it's going to be more likely for the attack to be successful. So we wanted to kind of make sure that we try to kind of give it a little bit more of a range of weight values. Depending on that range, we want to do some statistical evaluation of the range going over multiple iterations. And depending on that range, we add a little bit more noise or a little bit less noise. So the much larger range requires a little bit more noise. A narrower range requires a little bit less noise. And then in terms of self-adaptation, we wanted to gradually decrease the likelihood over multiple iterations for the actual insight that pre-trained models are less likely to be attacked. So over future iterations, later iterations, you have more or less of a pre-trained model. That's why we don't have to protect it more. So because of that reason, we will basically try to gradually decrease the actual likelihood of getting the weight perturbed. And with every single local gradient descent, we will try to decrease the likelihood of perturbing the weights. And with that very simple idea, it's just like one page in the paper. It's a very simple idea. We are able to achieve a very good result. So here, the red curve at the very top would be the curve with no defense whatsoever. The other curves are mostly the defenses of existing papers. Some of them, the performance is so bad in terms of converging to a good accuracy value over multiple rounds of learning, we're gonna have to plot this figure by going to break the figure in the middle and go to the extremes just to show how slowly the other defenses actually converge. So they might be effective in terms of the defense, but they completely destroy the actual accuracy or the speed of converging to a different accuracy, to a good accuracy. And our approach, which is the black line, the outpost, which is the black line, is the best performing. It's very close to the no defense. It is way better than, for example, differential privacy, the DP, the red yellow line. It's way better. And which, for example, differential privacy can only converge to a much lower accuracy. And by the way, no matter what it is, it turns out the accuracy is not very good. Even no defense, the accuracy is something like 50%, 55%. It's not very good. And this is not really related to, the actual gradient leakage attack. This is about the, overall deficiency of federated learning in general. All right, so now let's take a look at the actual figures, the reconstructed figures. Without defense, assuming, again, we assume everything that previous papers assumed is true. We have just one batch size of one, with just one epoch. We just have one data sample rather than a lot of data samples. All of that assumptions is true. We have access to gradients rather than model updates, everything. Without defense, we're able to reconstruct. However, all of the others, some of them, they use some of the metrics such as the MSE, and so on to actually evaluate their effectiveness. But if you actually look at the actual figures, you can see, regardless of these values of metrics, they all look pretty much the same. In other words, they are all very well guarded. The privacy of these original data, they're very well guarded, and defense are equally successful. So that's the issue. And if we change to a different data set, we're going to get the same result. So regardless of the numbers of the performance metrics, it's exactly the same in terms of the protection. Now, moving on to, before we move on, let's just quickly summarize. We have done a thorough investigation of gradient leakage attacks, and we wanted to point out that in federated learning setting, it is significantly weakened compared to the centralized setting. And we are able to come up with a lightweight defense mechanism even if we assume that we need to defend against this. But my personal opinion, no, we don't need to defend against this because all of these assumptions, they are not valid in the federated learning setting. So far, the data is safe. The privacy is well guarded, and even if it's not safe, we just need to have very minimum sacrifice to have a defense mechanism, very lightweight, and we will be sufficient. But what about other neural network models? Here we're using something very simple, like a very simple MNIST, fashion MNIST. These are simple convolutional neural networks. But what about deeper neural network models? ResNet, for example, deeper with more layers, and eventually, large language models. And why did existing papers actually claim that the data reconstruction attacks work? So we actually looked at these papers, especially the 5 papers that we have listed in our slides. What's going on there? Why do they really have a valid data reconstruction? So we ran the paper's code. It's great that they have open source code, and they all performed quite nicely. And however, what we did was we re-implement the idea in our own framework, and it turns out that the result will be dramatically different. There's no successful data reconstruction. And that's really strange. And I was working very closely with my student who wrote this paper. I'm basically saying, why? Why are the existing papers' code working and my code that we just completely rewrite everything is not working? So we compared line by line. We kind of say, okay, this line may be a little bit mismatched. Let's move them, migrate from the original code. And still, our code do not work in terms of data reconstruction. And finally, after quite a long time, we figured out a little problem. And there's a technical mistake in their implementation. And what is that mistake? Well, the mistake in their implementation, especially, for example, the NeurIPS 2020 paper, NeurIPS 2022 paper, what they did was that they did not really implement federated learning. They kind of simulated federated learning by doing everything in a centralized way, which is fine. You don't really have to communicate over the network. But it turns out that our framework, our own framework, we are trying to communicate over a network before we send to the server. So that's why we have separate. We have the server and the client completely in separate components, and they are only connected over the network. Over their code, they're not. They're actually in one PyTorch code. And it turns out that in that code, they have this model.eval in the client side. And that's something we'd spend a lot of time trying to figure out. We compared line by line, and finally we found out they're putting model.eval on the client side. And what is model.eval? Well, model.eval basically put the model in evaluation mode. And that is obviously designed in PyTorch to evaluate the model. We need to do inference on the model. So a few special layers, they will function differently. And we're going to get to that in the evaluation mode compared to the training mode. But why would the client do it in evaluation mode? The client is training with private data. Of course, it should put the model in training mode, right? So if we change it to the training mode, this is going to be a problem. It turns out on the server side, because the attacker had full control of the server, it's an untrusted server controlled by the adversary, the attacker will be able to use whatever mode. So either the training mode or the evaluation mode, anything is fine for the attacker. It's the attacker can feel free to do whatever they wish on the server side. But if we do something like this, we find out that if we start to actually change the implementation from the original implementation, we actually find out that things start to change. With the untrained neural network model as the starting point, even with this one episode, a batch size of one data sample, all of that, unrealistic assumptions, it turns out that by changing that one line of code, by putting the model to the training mode on the client side, we are not able to reconstruct any data at all with ResNet 18, which is, or ResNet 152, which is like a deeper convolutional neural network model. And it turns out that if the model is a pre-trained model, it actually worked out a little bit better. It's still not reconstructing everything, but it's a little bit better than the untrained model. It's this way. In this case, the table is turned in the sense that the untrained neural network model is actually harder to reconstruct if you change that one line of code in the source code, which is obviously a technical mistake. Now, this is a technical mistake, but it's not really a bug in the sense that a lot of the authors, they realize this line of code, but they realize that if they change this line of code, the reconstruction will fail. That's why they will put that in. And there's an evidence that there's one author actually put it in the appendix, in the footnote, saying that this is actually something that they did, which means that they realized that this is something that is the trick to make reconstruction work. Here's another example of the effectiveness of various defense mechanisms against this kind of the state of the art in terms of the gradient leakage attacks in the federated learning setting. And again, we wanted to look at our defense mechanisms. And it turns out that all of them, they're pretty strong in terms of defense. Outpost is no different from differential privacy and so on. So we are still able to defend against the attacks. But the question here is whether or not the attacks would be successful. It turns out that, it may not even be successful to start with. But our defense works even for pre-trained, deeper convolutional neural networks, where if we assume all of the unrealistic assumptions, it's going to hopefully be effective enough to defend against these mechanisms. So that's a very interesting discovery. But the question here is, we're no longer using convolutional neural networks these days. We're using transformer models. What about these transformer models? What about the so-called large language models? And will they have the same issue? So with large language models, we're no longer doing anything on images. We're not trying to reconstruct images. We're reconstructing the text. And this is equally important, obviously. We want to preserve the privacy of text, which is the input for training these large language models. And the question is, do we still have the same problem? And so we looked at the existing papers that claimed that large language models reveal the privacy of data that we use to train these large language models. And we found out that, unsurprisingly, the same technical mistake exists in their code as well. Maybe because that without this technical mistake, it will cease to function. The reconstruction will not even work at all. So what about this technical mistake? What's the effectiveness of putting the model to the evaluation mode in transformer models? Well, in transformer models, we have the actual dropout layer, typically. And that's something that is typically used in transformer models. And it turns out that if we actually try to put it in training mode for the model, the dropout layer is going to drop. From the name, you can infer that it's going to drop out, a portion, a percentage of the actual input, just to make the actual training loop a little bit more or a lot more robust. But for the evaluation mode, obviously, we don't want to make it a dropout. That would be insane. We're going to make it a like all pass filter. Everything will be passed through that particular dropout. So there's a major difference between evaluation mode and the training mode. And another example of a particular module or layer in the model would be the normalization layers, batch norm, instant norm, and so on. And the batch norm is very typically used in convolution neural networks. And in training mode, we're using per batch statistics. And in evaluation mode, we're using the running statistics. So this is something that is in the CNNs. And this is actually one of the reasons why something like ResNet, there's a major difference between evaluation mode and training mode because of the differences of the evaluation mode and training mode for these kind of normalization layers. So now let's look at some of the results. We have 3 different cases, A, B, and C. A is putting the model in the evaluation, and then we try to get everything to work, which is in the other original implementations of existing papers. B is to do the right thing, put the model in training mode on the client side, and then try to produce it. And C is to, on the client side, we do the training, but on the server side, we use the evaluation mode, which is up to the adversary to do. So if the ground truth is a certain sentence, for example, the problem easy to solve the question, any sentence, you don't really have to read the actual result in terms of the English. I have labeled them for you. So if you just look at the purple highlights, the more purple it is, the more likely that the adversary will be able to get the original sentence, in the sense that it's actually closer to the original sentence. For example, A would be the question, the problem solved question is easy. So, the term, the question, or the problem, or easy, all of these are reconstructed. And that would be obviously something that we could call it a successful attack. But if you actually get started, try to move to, B and C, it's going to get harder. You can see it's going to be less purple as compared to the original. And of course, if the ground truth is something very simple, we still have a possibility of getting it. But once the ground truth is getting a lot more longer, you can see that it's getting harder in the B and the case B and case C to actually get the original data. In fact, case B and case C, even though there are still some purple, you cannot really decipher it to see what the original sentence is trying to say. Even though there are a little bit of overlap in terms of repetition of words, you cannot see what's going on in B and C anymore. And again, this is something that is assuming that we have, very idealistic assumptions. Batch size of 1, we have access to gradients and everything. We don't. In federated learning, we don't have access to gradients, and we don't have a batch size of 1. We don't have just one epoch. We have completely realistic cases. If we start to move to looking at gradients, to looking at model updates, in this case, let's call them deltas. These are not gradients. They're kind of accumulation of a lot of different iterations. Model updates, the differences between the new model and the previous model, you can see that completely defeats the actual data reconstruction attacks. Nothing is purple in the other areas, in the delta case and for all 3 data sets. And if we actually try to do something like a LoRa fine-tuning, which is our pretty much the de facto standard of fine-tuning a pre-trained model, we will see that it's getting even worse. for example, SSD2, you still is able to reconstruct one word, sort of. It doesn't make sense. The sentence doesn't make sense, but you still get one word. But in LoRa, nothing happens. So LoRa is even stronger in terms of protecting the original data. For different cases, we tried, for example, one episode, the batch size of 2, we get the same results. The delta now is becoming even worse in terms of the result of reconstruction. Nothing can be reconstructed. In LoRa, the same thing. Nothing can be reconstructed. And it's pretty well regarded, pretty well guarded in terms of the original privacy of the data. And the same applies to anything else. For example, if you have just 2 episodes and the batch size of 1, again, these are very unrealistic. Typically, we have at least 5 epochs, and then a batch size of way more than 1. And, we basically have no reconstruction at all in terms of the text input to a large language model. But malicious model manipulation is a more recent discovery of existing papers. So what do we mean by malicious model manipulation? So here, we're assuming an even stronger adversary. So that the adversary not only can kind of doing this honest but curious kind of a threat model by looking at the data and looking at the gradients or looking at the model updates and reconstructing the actual data, they can manipulate the model. As you can see in the original case of federated learning, we're sending model updates, the model from the server to the client. So what they assume is that when we send the model to the client, we can change the model just a little bit so that we could induce some kind of a leakage of private data on the client. So the unsuspecting clients, they would be able to take this kind of manipulated model, like a compromised model, unknowingly send their private data, try to fine-tune it or train it, and try to send it the model updates back to the server. And in this case, the server, as claimed by the papers in the literature, they are more likely to leak the private data. It's easier for the server. As you can see intuitively, of course, if you have the ability to manipulate the model, it would be easier to leak the private data. So that's the claim of the existing papers. And however, again, they're making some simplifying assumptions. This is one example of this is called privacy backdoors, published last year, ICML. This basically is a backdoor model. The model is manipulated, and what they claim is that they have, again, we looked at their source code, and they actually assume that the optimizer that is used on the client is a very simple one. It's just, stochastic gradient descent. And that would be very, very simple optimizer that nobody uses these days, right? So that's what they assume. But what if we don't assume that? What happens if we don't assume that? So this is stochastic gradient descent, and the update rules, if we do not assume anything about the momentum, the weight decay, the learning rate of the scheduler, and everything, then you can see this is a linear relationship. It's much easier to reverse engineer and get the data. So that would be the essence, the essential thesis of these papers. Basically say they take advantage of this kind of update rule. But what if we add momentum? What if we add weight decay? We add learning rate scheduler, all of those. And on top of that, more importantly, what if we change the optimizer to something that everybody is using these days, which is, for example, Atom optimizer? The Atom W update rules would be way more complex than the SGD. Can we still reconstruct the data? Even if we allow the adversary to manipulate the model on the server. So what we did is that we simply switched the optimizer and from SGD to Atom. And the original paper used kind of like an outdated transformer model, the BERT model. I wouldn't call it out of date. It's just not used in modern large language models. We can still use them for some special purposes. But the original BERT model was an encoder model rather than the decoder only. It's an encoder-decoder model. So this is something that they use in the original paper. So we kept using them. as they did in their original paper. We just moved the SGD to something a little bit more practical. So the original SGD, as the original fixed, SGD is in the original paper, so we can reconstruct the sentence. In other words, the original paper was making the right claim. Nothing's wrong with their claims, except that if we start to manipulate the SGD to something that is having momentum, then the reconstruction starts to break down a little bit. We can still reconstruct quite a bit from the original sentence, the ground truth sentence, but it starts to break down. But starting from Adam, everything breaks down. Whenever you switch to Adam rather than using SGD, there's no way that you can reconstruct the data. So that would be an interesting experiment in the sense that nobody's using SGD anymore, especially we're talking about transformer models. We're using something way more modern. And it turns out, well, Adam is proposed back in 2015. It's not really like a new optimizer. No, it completely destroys the adversary's ability to attack with a compromised model. But the original paper, basically, you assume the BERT model, which is like a encoder-decoder model. But let's say we're using something that is more modern, which is more of a decoder-only large language model that, our modern large language models use. Let's say we use something very small, which is GPT-2. Typically smaller models make it easier to reconstruct. Let's just say GPT-2. It's a decoder-only model. It has all of the essential elements of a modern large language model. And it turns out that over here, we have the squares, we have the boxes, boxing up the actual words that are repeating from the original ground truth sentence. And we have the underlines to show something that is similar, but not necessarily repeating. But you can see, if we start to use GPT, even the original SGD, the actual effectiveness breaks down. It turns out that GPT, the decoder-only model, as compared to BERT, is much more resilient to these compromises in the actual model. However, if we move to Adam, it's even worse. So Adam is much harder to reconstruct the original data. So it turns out that this is something that we found out that GPT-2 is actually, much more resilient than BERT. So the conclusion was that if we use federated learning, and if we use private data on the client side, and we try to train using private data on the client side, no matter what the adversary does, whether or not they can compromise the model, whether or not they can get the model updates or the gradients, as long as we don't make completely unrealistic assumptions, the data privacy is indeed preserved. That's my personal take of this, which means that you really do not really need a lot of these very expensive cryptographic methodologies to actually protect the privacy of data in the federated learning setting. And what about training while preserving privacy? Is it feasible in practice? And I believe it is. You could actually try to train while preserving privacy, which basically is what we studied in the past. Gradient leakage attacks are not effective in any practical sense of federated learning. That's what we assumed. And on top of that, more recently, we found out that parameter efficient fine-tuning, the LoRa fine-tuning, further limits the effectiveness of data extraction. Even in non-federated learning contexts, even in centralized machine learning, we found out that over here we have a few different ways of evaluating whether or not data can be reconstructed. We call it memorization. So different ways of evaluating memorization, how well the model can memorize the actual private data. It turns out that if you actually have full fine-tuning, it's the memorization, depending on how you evaluate it, you can use different ways of evaluating this. But regardless of the way of evaluating this, the red dots are the ones with full fine-tuning, and the blue ones are the ones with LoRa. As you can see, the LoRa is way more effective protecting the privacy of data compared to full fine-tuning, even if we are not using federated learning. Even in the centralized machine learning context, you open the weights of the model, you try to see if you can reconstruct the data. Existing papers, they say, okay, I have full fine-tuning, maybe I would be able to, it's still debatable because I'm not too sure these memorization metrics are valid enough. If you look at the original text, it may not be valid enough. But if we switch to LoRa, everything's gone. We don't really have the compromises anymore. Data is fully preserved in terms of their privacy. We also have different duplication levels. So if you actually duplicate the data, so a lot of repetition in the original data set for the actual fine-tuning data set, you actually get more memorization. However, if we actually try to deduplicate the data first, try to get rid of the duplicates before we do the fine-tuning, even with the full fine-tuning, we still cannot do the memorization, not to mention LoRa. So that would be extremely important for us to find out. And we have open sourced everything that we have done. This talk, even though it's kind of short, it's a combination of 5 different papers. Some of them are unpublished. They're still under submission. And a lot of them, they're open source and they're in the GitHub already. It's part of my open source framework called Plato for federated learning research. It's very easy to use, well documented. I encourage to use it. I wrote most of it. And all of the code that we have is part of this open source framework. So that's everything I have to say. Thank you so much. Welcome.
Okay, so any questions?
Turn off the light?
Oh, yeah. Okay, question?
Yeah, I think this is one of the most interesting topics. Thank you so much. I'm very interested in this model trend stuff. You mentioned that you have some paper published already. I was kind of wondering what is the real comments. Right? What's their opinion? Because this is obviously not a small thing. It's actually many papers are based on the original application. It could be wrong.
So all of the papers who show effective data reconstruction, they are based on that. Because if you don't do the model evaluation mode on the client side, there's no way that you will reconstruct. You have to do it. So our papers who actually refute this claim was published in IEEE Transaction Networking and IEEE Transaction Big Data. Our reviewers are favorable, so they like our paper. But I'm not sure about the review comments of the other papers who actually published these papers from existing papers. But I very much doubt that the reviewers go this kind of level of detail because we actually spend a huge amount of time looking at the source code, right? So it's very difficult for the existing reviewers to look at anything. But it turns out that it's changing the results. All of these are changing the conclusion, completely 180-degree change. So that's going to be quite interesting. And I believe that we should not use those papers' conclusions as the foundation for our, for example, defense work or cryptographic algorithms or things like that. We should not use those conclusions because those conclusions are questionable. At least we should take that. Yeah, that's a take-home message.
I assume there's still many papers already there once and getting published.
Yes.
I was like, in this kind of situation, what would you take away? What can we ask, academic researchers how to avoid such kind of thing?
Right. Well, we cannot avoid this because out of all of these papers that are published using this bug or this technical mistake, only one paper mentioned it in the appendix and in the footnote of that appendix. So it was not really well documented that they're actually doing this. This is actually the key to they didn't say that. They basically say, oh, here are my results, which can be repeated, by the way. They open source, which is great, and can be repeated, or everything can be reconstructed for sure if you actually make that mistake.
Thanks for follow this question. So if all the reconstruction happens when the mistake exists, does that mean in a real world federated system, actually there's no such a problem?
So
doesn't exist.
Exactly. So my point, that's exactly my point. Because in the real world federated learning, clients, they do not put models in the evaluation mode. They put them in training mode. Not to mention that they're not sending gradients to the adversary, they're sending model updates, right? So all of these are realistic, practical federated learning practices, best practices, we can call them, in federated learning. And in these cases, I don't think there will be a good data reconstruction. There's no way you can reconstruct the data at all, in fact.
I think that's also the reason the Boltrini writes the federated system by himself. It's called Plato. He spent 3 years to write this code by himself.
Yeah, this means like a research direction is closed.
Yes, which is good news, by the way, because you wanted it to be closed. You don't want federated learning to add differential privacy, for example. If you add differential privacy, the performance of the final converged trained model is going to be not very good. In fact, it's not good at all. No matter how much noise you add, just a little bit of noise, it completely degrades the accuracy of the model. And it's good news that the data privacy is preserved, because now we could use that as a real motivation to motivate federated learning, rather than saying, no way. We have to add a differential privacy. We have to add another defense. We have to add homomorphic encryption, fully homomorphic encryption or something to actually protect against these adversary attacks. So I don't think we wanted an efficient implementation of federated learning without any of these compromises, even if the server can manipulate the model.
Yeah.
So I remember you show a lot of model comparison. I wonder, because you have a cutoff, because the word time is so long, and I see that the model you referred was not doing very well in the beginning of the training. What's the reason?
Let me switch to that and see if I can get to that. To share this. Right, so this is the figure that you're talking about, right?
Yeah.
Yeah, so in fact, if you see that the black line, which is the outpost, actually it tracks the red line very well. It's the differential privacy that did not work. Differential privacy did not work. The green line, which is so-called grad defense, the InfoComm 2022 paper. The purple line is the worst. It's called Soteria. It's a CVPR 2021 paper. It's even worse. So, so the other lines are the ones that are no good. The black line is very good. It keeps track of the no defense line very well. It loses a little bit of accuracy towards the end, but not that by a whole lot.
I apologize. I thought the purple line is outpost. Sorry.
Yeah, it's the black line is the outpost. The purple, yeah, it's hard to tell, but because it's easy, hard to tell the figure, the colors. But the no defense is the top, at the red at the top, and the black is the second best.
Yeah, actually, I'll ask another question first. So, even though plateau accuracy is below 60%,
exactly.
I'm not sure about the task. Like, is it desirable, or you want to improve it further?
So this is actually a very good question. This is it's obviously you cannot really improve it further. And that is not because of the defense. Obviously, the no defense also converges only to 55%. It's actually, by the way, this is CIFA 10, and the ResNet 18 model. It's a relatively simple convolutional neural network model, and relatively easy to converge, kind of like an image data set classification task. And the problem here, which is a fundamental problem, is the problem of federated learning itself. Federated learning very, very much degrades the performance of the trained model because it's doing weight aggregation. And it's not aggregating every iteration, obviously, because of the fact that you're doing local training for quite a lot of epochs. It's aggregating after several epochs. And you can imagine that local data, they're actually going to different directions. And once you aggregate, none of them is actually mixed. The result of aggregation would be something that is not resembling any of the local training. So that's why the degradation of the final converged accuracy. In this case, if you do centralized learning, ResNet 18 and CIFAR 10 can easily converge to something like 85% or even higher, to do this. But if you do it feather learning, you're going to have to stay with something like 60%, 55%. You cannot go beyond 60%. If you add differential privacy even just a little bit, it can even be worse. So this is the problem of federated learning. It's not a problem of this, but this is a problem that needs to be solved. In fact, some recent work from DeepMind last fall, they actually tried to propose some replacement of federated learning and actually try to solve something like this. And try to do this hopefully a lot better.